Okay, let's go on. Can you hear me now? Okay, all right, let's go on now. All right now. Okay, so we have, now that means I cannot see the chat at all because I'm on the full screen. So you will have to yell or some way let me know that you are, somebody had a question. Okay, so I see nothing except this whole screen in front of me. So we have already figured out that indeed your train or spaceship going at 0.8 times the speed of light, which is very fast, actually now appears to be shorter, 600 feet. Therefore, I can now say that you, as a train moving so fast, you can actually be confined or trapped inside my tunnel. Why? Because my tunnel is 800 feet. My tunnel is 800 feet, but your spaceship, your train, is only 600 feet. Okay? So I can now do the following. You are traveling at 0.8 speed so that the Lorenz contraction allows it to fit entirely inside the tunnel. You came in, zoom, you came in, right? And you came in and you are now short enough within my tunnel. And then you know what I decided to do? That I will now slam the door, trapping you. How? Because I tell my engineer, when you see this train, the front end pass in, and then you see the back end pass you through here, close the door, shut the door. So when the engineer who is down here sees that the front of the train came by and the back of the train also entered, slam. And then at that same instant, when you slam this, the front end of the tunnel also slam. Therefore, for some 125 nanoseconds, you actually trap this train. You got the idea? It's a very interesting Gedanken experiment. You now say, I want to trap this. Why? Because your length, even though you claim that your length is 1,000 feet, but because you're moving at so fast, 0.8 times the speed of light, your actual length is now contracted. Professor Albert Einstein already figured it out, and Lorenz had also figured it out by using something else. That's why it's called Lorenz contraction. So now the length of your train is shorter than the length of my tunnel. Bingo, I have trapped you. And of course, if I don't let this door up, then there will be a disaster, right? Because if I close the front and the back door, and you are going at 0.8, see, 125 nanoseconds later, you will be here and you will crash against this. But then I will tell my engineers and say, when the front end is coming near, then please open. And so you say open, and the train just zoomed right through. So the interesting thing about this train in a tunnel paradox is that indeed you can trap a train whose length, whose own rest length, whose own proper length is longer than a tunnel, but for a very short fraction of a second, you can actually trap it. Now, supposing indeed you were good and you have already told your engineers and they indeed open the thing so that no disaster happens, the question that you can ask for those passengers on the train, you can say, what happened? Right? This is just simply using Lorenz contraction to make use of the actual Lorenz contraction and to say, in principle, I can trap you. And yet no disaster happened. How do we now explain it? We now ask the guy who is on the train. All right? Are you okay with this? we have grasped the concept of Lorenz contraction. You were originally 1,000 feet, but because you're moving so fast, your actual length, as far as I'm concerned, I'm the observer, as far as I'm concerned, you are now shorter. You are not what you claim to be 1,000 feet. You are only, 600 feet? You're only 600 feet. And therefore, I can trap you. Now, from the train rest frame point of view, what does he see? Well, from the train, he will say that your tunnel is not 800 feet. Your tunnel is not 800 feet. Your tunnel is actually 480 feet. Why? Because there is also a Lorenz contraction of the tunnel as far as the guy on the spaceship is concerned, on this train is concerned. You claim that your tunnel was 800 feet. The Port Authority people say, oh, we paid the contract to dig a tunnel, and the tunnel, they say, according to the contractor, was indeed 800 feet. But the train guy says, I don't know. I did my own measurement because I am on the train. And then I say, when did the front end of the train pass me by? And then when did the back end of the train pass me by? And I now know that there is this Lorenz contraction applied to your proper length. Do you see it now? You got to be very careful here. You said you built your tunnel 800 feet. But me, I'm on the spaceship. I'm on the train, which is so fast, it's really a spaceship. I'm on the spaceship, and I'll say, your tunnel that you say was 800 feet is not 800 feet. It is 480 feet. Why? Because your tunnel, to me, your tunnel is moving. I'm at rest. It is you, the tunnel, that's moving. And your length, as far as my own rest frame is concerned, because I'm on the train, so I am the train's rest frame. As far as the train's rest frame is concerned, it is not 800 feet. It is only 480 feet. All right? And now, how do we now explain away this near disaster that did not occur? The near disaster that it almost could have but did not occur. Well, what is the sequence that the train conductor will say? Well, the train conductor will say, the front end of my train entered your tunnel at, let's say, I don't know, 12 o'clock, according to his clock, right? At 12 o'clock, the front end opened up. And so the train entered. But when the front end of the train came to the other end of the tunnel, my back end is still outside. The train conductor says, when my front end of the train entered, and then when it came to this end of the tunnel, my back end is still out there. And your door did not close yet. Then when it reached here, you had closed it, but this one was still open. It was not simultaneous. You said simultaneously it should be open, simultaneously it should be closed, right? Your tunnel people, the engineer says, I have made it simultaneous. It will open and close at the same time. But the train conductor says, no. This one opened first, and the front end of my train came, and then when the front end was nearing the back end of the tunnel, this then opened, but this one continued to be open I mean, this was closed, but then when it came to here, it opened, and this remained open, did not close until the back end come in here, and then the back end closed. Are you able to? I guess there should have been more pictures of this in the sequence of front end opening, back end opening. Do we need to go through this just to get that picture clear of simultaneity, that it's no longer simultaneous, and the sequence of events? I wish I could animate this, but I don't have. I downloaded it from some Illinois University Urbana, where they have made this beautiful slides. But the sequence is, your tunnel was totally closed, both doors were closed, and my train was coming, zong 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 zong, right? And then the train conductor says, and then what happened was this door opened, and so my head of the train went, and now this door didn't close yet, but now this door that was locked was open, so that my front end now passed through, but now the back end this door did not close yet, did not close until my back end was in there, and then you closed it. But that's okay. My front end was already out, and my back end was now coming along, and when I am fully out, then you close this and you close that. So the sequence of events of opening and closing are not simultaneous as reported by this observer on the train, by the conductor. Do you see the interesting aspects of this? I wish maybe I should have downloaded the video showing it, but there was a question. I can't see who has the question. With this desktop, I don't have my laptop to go with it, so I cannot see. Did somebody have a question? At least can you sort of appreciate the two different accounts of a near fatal but non-fatal event? And the non-fatal event, from the ground point of view, was that you came in and you are short enough that you were for 25 nanoseconds, you were actually all within the tunnel. And what I did was I opened it for you so that you can enter. I opened both front and back for you to enter, and then I closed the two, front and back, for 125 nanoseconds. And then I told my engineers to open, so that indeed there was no fatal crash. You actually went all the way out. So that was the sequence. This was always simultaneous. Closed first, open simultaneously, and then closed simultaneously and open simultaneously. So there were these sequences, but yet from the point of view of the conductor, he says the sequence of events is different. And it was just nice. When my front end of the train was coming, it was originally closed, but when my front end was coming, oh, you people were so nice, you opened this. Well, when you open this, my front end goes in. Well, this was not open yet. And when this front end of the train is coming here, when it approached, oh, you open this, so that I could then go out. There was no crash. But when my front end was here, my back end was still out there. But it was so nice of you that you did not close it. And only when my back end is now into here, you then close it, but that's okay. My front end was out already, and this is still open. And then later, this thing, when the back end is now fully, what you call, over here, there was no crash. This one is already all way out, and the back end is now clearing the tunnel. I may have overworked you by describing to you this train tunnel paradox, but it's okay. It's fun. Einstein's Gedanken experiments are usually very fun because you are thinking outside the box using whatever is the postulates of relativity. Any questions or comments? Yes or no? I cannot see any chat. I'm not mute, right? You can hear me.
Yeah, I can hear you.
Okay, all right. So now let's go on. But you are kind of very soft, but okay.
So, Professor, so the size of the train gets reduced.
Say that again.
So the size of the length of the train gets reduced when it's traveling at the with the
Yeah,
speed of
right.
speed of
That's right.
light.
That's right.
Okay.
The length of your train or the length of your spaceship is contracted when you are flying past me. I am here. I see you passing by. Your spaceship originally was supposed to be, what was it? 800 feet. Your spaceship, or 1,000 feet. Your spaceship was supposed to be 1,000 feet. But because you are moving so fast, I will now say your length, as far as I'm concerned, is shorter. It's now 600 feet. So this is Lorenz contraction of any object whose proper length, whose rest length is so many, let's say 1,000 feet. But because you're now flying through space, the guy who is observing you will say, oh, this spaceship that flew by, oh, it's only, 600 feet. Okay? Okay, so now let's go on. Now we got to come back to momentum, which we already touched upon. In non-relativistic, momentum is P is mv. But now relativistic, Einstein has worked it out that it is now bigger. And this effect of it being bigger is more dramatic the faster your speed. The closer you are to the speed of light, oh, your relativistic momentum is now so much bigger. But if your speed is only so small, then there's not much difference between the relativistic momentum and non-relativistic momentum. Because if v is only 30 miles per hour, this factor is negligible. All right, so we take this as a, and then I already covered this, so let me just quickly remind you that on the West Coast at Stanford, Stanford Linear Accelerators, they have built a long tunnel. It's about 3 kilometers long. That's about 2 miles almost. 2 miles long. And what they do is they have boosters, electric voltage boosters, to boost a voltage difference, not of 100 volts or 200 volts, but of so many billion volts. Right? So in other words, they go by steps. this goes to 1,000, and then another a factor of 1,000 and 1,000 and 1,000, so that over 2 miles they are able to build it up to so many billion volts, and therefore the energy that it acquires is the charge times the voltage difference, and the charge for the electrons, of course, electron, and you call that electron volt, that this is now so many billion electron volts. And they are able to do this in order that what they want is for these electrons that have such very high momentum that they will crash to a target. If they will crash to a target, it can then spew forth the extra particles that are part of matter. So they would want to have quarks, that they can produce quark, anti-quark, and so on. We will not at this point go into it. We just simply say that that is application of relativistic momentum of Einstein. And they give you some numbers, but you don't have any sense of how big is this momentum, because we are not used to dealing with these very small mass and these very high velocity. So don't worry. It's just that since the book has it, I reproduce it for you. But what is more important is this, because in the end, we all know Einstein is most famous, not just for relativity, in terms of special relativity, in terms of general relativity, but the most important formula that he is famous for is E equal to mc squared. That if you have a certain mass, then you actually have so much energy, and this is called the rest energy. And if you are moving, the total energy is even bigger. So this is called the rest mass. This is sometimes called the moving mass. That when you are moving, you now have a mass that is bigger versus when you are at rest. And this is the very famous formula E equal to mc squared. And he first figured it out, as I mentioned, while working in the patent office in Switzerland. Well, from here, you can now look at the kinetic energy. The kinetic energy is the difference between the total energy versus its rest energy. And now you can work it out. And you can say, okay, if I take this formula, I take the difference. That's now this formula, mc squared, 1 over this factor, 1 minus v squared over c squared minus 1. So for v very small, if v is 0, of course, there is no kinetic energy. But v is small, you can then use the algebra to figure out what is the formula, and we will see it. But first, since the book has this example, let us look at this example. You have a golf ball. Golf ball is a small mass. What's the mass of a golf ball? 0.046, namely it is 46 grams. All right, it's a small golf ball. Of course, I wouldn't want that golf ball to hit my head, but it is a small mass, 0.046 golf ball. It's lying on the green. If the rest energy of this ball were to be used to operate a 75-watt light bulb, how long would the bulb remain? This is sort of, again, like a Gedanken experiment. It's just simply curious. If you tell me that if I follow Einstein, and it is a certain rest energy, E equal to mc squared, I want to now figure out how much is this energy And what if I were to able to convert that energy? And it's not a trivial thing to say, gee, you give me this golf ball, how do I convert this energy into light? Well, even the experts at the moment cannot do it without smashing it. And then when they smash it, they cannot really use it for electricity. It's pieces. But anyway, let us just go through this Gedanken exercise. And we say, okay, I know the concept you're asking is the rest energy. And then I look it up in my PowerPoint. The rest energy is mc squared, where I know I have to use the metric international units. So I have to use kilograms. I have to use kilograms, and I have to use meter per second for the velocity. And then this would be in joules. So that's just to remind ourselves, the units. I don't know why my cursor keeps coming and disappearing. Where's my cursor now? Oh, okay. So I will now work it out and say that m, you told me, is 0.046 kilogram. And the velocity of light is 3 times 10 to the 8 meters per second squared. And if you work everything according to these international units, then the answer is in joules. So you work this out, and this comes to be 4.14 times 10 to the 15 joules. That's a lot of joules. But we still don't quite appreciate what does that mean, that it is 10 to the 15 joules. Well, you have to then remember from, must be 203. You remember the power is the rate at which work is done. If this is the total energy and the power is 75 watts, then the length of time it takes to do this much energy is the power times time. That's from 203. Okay, so I now write T, the time where my light bulb will continue to shine at 75 watts, is E0 over P, the average P, which is 4.14 times 10 to the 15 divided by 75 watts. And if I work out the math, it gives me 10 to the 13 seconds. Well, that still doesn't impact, because you say, gee, I know in seconds, but you're dealing with 10 to the 13. I know it's a long time, but how long is it? Well, you then have to look up that 1 year is of the order of 10 to the 7. It is, I don't know, remember whether it's 2 point something or something, around 2 or 3 times 10 to the 7. Therefore, this light bulb, if you are able to convert all of this rest energy into electricity, it can keep my light bulb on for 10 to the 6 years. Clearly, if some genius can actually do this without smashing up the whole world, that would be a beautiful thing, because there are enough golf balls around, right? But this is just a Gedanken experiment or question. Are you okay with this Gedanken experiment? Okay, all right, now let's go on. And now the other question is, gee, what if I now go back to Stanford linear accelerator, and I have an electron whose mass is so small, 10 to the minus 31 kilograms, very tiny. It's accelerated from rest to a speed of 0.9995 c, because the SLAC accelerator, they really boost up the voltage to a very, very high, so that the velocity now is very high. The energy of this electron is very high. So now they want to know, first, what is the electron's rest energy? What is this total energy? And what is this kinetic energy in millions of electron volts? So we just go back to the basic formula, E0 equal to mc squared, and then we work it out in the metric units, in the international units, and this then says that it is 10 to the minus 14 joules. You remember the golf ball was 10 to the 15 joules, but one electron only has this much small amount of joules. That's because the mass of the electron is so small. The golf ball was 0.046 kilogram, and therefore the amount of energy in the rest energy of an electron is very small. 1 electron volt is 1.6 times 10 to the minus 19 joules. These are in the metric units, engineering units. So many joules. The electron rest energy now you can convert, and it is equal to 0.511 MeV. So the rest energy of the electron by itself is only so many 500,000 electron volts. But you remember I said for SLAC, they wanted the electron not to have 500,000 electron volts. They want to give this electron boosted up so that it is so many billion electron volts, gigavolts, GeV. Well, that means that you really have to boost it. But for the moment, they are just simply asking, or you have to boost it up to a very high speed. So now they want to say, what is the total energy when you indeed were able to boost it? Boost it so that its velocity is now 0.9995 c. Well, we now go through the exercise. We go back to one of the PowerPoint formulas and they say, oh yes, the total energy, we are told that Einstein figured out, is mc squared over this. And now you put in the numbers. You put in the small mass of the electron. You put in the velocity of light, even more precisely, 2.998. And then you put in this v over c, knowing that it goes at 0.9995 velocity of light. And voila, it is now 16.2 MeV. This is not yet SLAC. This is so this velocity is not fast enough. SLAC, the electrons are going even closer to the speed of light. But anyway, this example that the book quotes is only 16 million electron volts. So the SLAC people will say, oh, this book, yeah, out of date. You're not representing SLAC well enough in terms of the kind of energy that they have. Well, the kinetic energy, given that this is so, you can now calculate. Oh, what did it do? Kinetic energy is E minus E0, and then you work it out, and it is 15.7 million electron volts. All right, so this is just giving some exercise on knowing what is the formula for the total energy. You can then ask questions about what's the kinetic energy and what's the rest energy. It's all just a matter of putting in the correct units for the calculation. Okay, any questions at this point? All right, and now this is another example. Well, it's an interesting example, so let's do it. You have the sun. It is giving off. It's basically a big reactor, and it is giving off radiation at the rate of 10 to the 26 watts. There's a lot of wattage. It's not kilowatt, it's not gigawatts, it's 10 to the 26 watt. What is the change in the sun's mass during each second that it is radiating energy? This is again using Einstein's concept of energy and the mass equivalence, right? You now say, if it is radiating this much energy, and we all know that because we have measured it on Earth, We know how far the sun is from the earth, and if it is radiating at 10 to the 26 watt as a spherical wavefront, and when it comes to the earth, we have measured it to be 1,300 and something watt per meter squared, the upper atmosphere. By the time it comes down to the ground in Arizona, it's about 1,000 watt per meter squared. Since I know that, I know what was the total wattage, because I know the angle that it subtends when it comes to the earth. So I know this. This I know because I have measured it, and it's an important number. I would like to know, during each second, how much mass has been converted, equivalent to it. Well, you told me that it is so many joules per second. That's what 1 watt is. And in 1 second, you divide by c squared. It means that the amount of mass converted to this, according to Einstein's theory, the amount of mass of the sun that has been used up to give you this much energy is 4.36 times 10 to the 9 kilograms. All right. And now, I thought it would be good to now compare, just for comparison. This much mass has been converted to radiation. You say it's 10 to the 9. That's a lot. But for our Earth, we are 10 to the 24. So you say, oh, that's okay. I don't worry. I don't worry that the sun is converting this much mass to the light, because it's not such a big number. This number is not such a big number compared with our Earth, for example. But now this amount, you now want to know, what would it be if you did this for 75 years? Well, if this is the rate at which you're using up my solar mass, my sun mass, if this is the rate per second, then in 75 years, it is 75 times 3.16 times 10 to the 7 seconds. Because in 1 year, there are 3.16 times 10 to the 7 seconds. And you do the math, it is 10 to the 19 kilogram. But then you compare with the mass of the Earth, it's still okay, right? You say, you have been using up, and in 75 years, you use up 10 to the 19, but the mass of the Earth is 10 to the 24. I don't have to worry. And so you can now say, what fraction is this compared with the mass of the sun? Well, you look up, the mass of the sun is 10 to the 30. Therefore, this fraction is 10 to the minus 12. So don't worry, the sun will be shining. And actually, if you were to ask, what would be the total number of years for the sun to have used it all up as radiation? You can do the math again. Or I did the math. The book did not do the math, but I did the math. At this rate, the sun will last 10 to the 13 years. Don't worry. The age of the universe, according to the experts, is 10 to the 13. No, 10 to the, how many? So many billion years. So it's 10 to the 9. So this is longer. It will last longer than the age of the universe. All right, just to tie up the concept of energy and mass. Okay, now that we have done such a lot, I want to now, the book also has that, so we'll just quickly mention it. That if you have a spring, the spring is massless, and suppose the spring is stretched or compressed, then the spring will have potential energy. And if the mass of the spring is still zero, when the spring is either stretched or compressed, according to Einstein's concept, the spring will now have mass. Even though originally it was massless, just for simplicity, the fact that you now have either stretched it or compressed it, it will then have mass. And you want to now know, is the mass increase because you stretch it, or whether you compress it or stretch it? And the answer is the energy change, the spring potential energy, is 1/2 kx squared. So it doesn't matter whether you stretch it or compress it, the mass of this, the equivalent mass of this spring now is still increased. Okay, then finally, let me just mention this relationship between energy and momentum. We have already said that momentum, relativistic momentum, is this. But we want to now re-express this equation algebraically. Here's the concept. Now I want to re-express it algebraically and say, I want to express it in terms of momentum relative to its velocity. So then m over this is p over v. All right, you see this is mv, so I have re-expressed this. But the total energy, you remember, is mc squared over this. Therefore, it is p over v times c squared. I'm going through the algebra here, right? I already grasped the basic concept, E, and the basic concept, momentum. I want to relate them, and I'm now using my algebraic strength and say that this, I can re-express it as P over V, which is m over square root 1 minus V squared over C squared, times C squared. And furthermore, I can write this as this equation. I can re-express it as P C divided by E is V over C. Do you follow? I basically separate out one C, push it up here, leave the other C out there so that this is V over C, and I move it over there so that V over C is equal to PC over E. You will have to sort of say that I can understand the algebra. You can afterwards look at the slide, PowerPoint. But now, when I realize this is my algebraic strength, I can re-express Einstein's formula as E equal to mc squared over 1 minus p squared c squared over E squared. Why? Because down here is V squared over C squared. But I have now already expressed this as PC over E. So therefore, now I have a more sophisticated, more complicated looking equation that says E equal to blah 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 over this. But then my algebraic skill is good enough. I can now re-express this as E squared equal to P squared C squared plus M squared C4. This is the overall relationship between the total energy and the relativistic momentum. It all came from momentum and energy, but now re-expressed so that it says, just like non-relativistic, you have a certain amount of energy. Well, that is related to your kinetic motion, your kinetic energy, and this says that the total energy of your electron is equal to your rest energy, m squared c fourth, because this is E squared. But when you are moving with some momentum, then it is in addition to the rest energy, there is momentum, kinetic energy. And we can now figure it out for low velocities just to see what is this equation related to. Well, I work it out for you, and I say for low velocities, let me first re-express this as E equal to mc squared square root of 1 plus p squared over m squared c squared. Namely, I take m squared c fourth out overall, put a bracket around, then this is p squared c squared over m squared c fourth, so therefore it is p squared over m squared c squared. I mean, we can do the algebra. And therefore, for small momentum, since I know what is my P, and P was this, for small momentum, it then becomes the expression, algebraic expression, square root of 1 plus something is 1 plus half of that something. And this, of course, is what we know, the kinetic energy. This is the relativistic kinetic energy, this is the rest energy, and this then is the total energy for low velocities. All right? I hope you can follow first the grasp of the concept, and then let the algebra take care of itself. Now I want, then the book has this last section, but I'm not going to, you will not be responsible, even though it is itself very important for Doppler shift, for relativistic motion, but I will not, we will not go over it. And the book also doesn't really spend much time on it, so we will leave it alone. I want to now come back to the history. You remember I said that Einstein gave a lecture at City College when he landed in America in 1921. I actually went through the website and found that it was not after the war, but it was actually before the war, 1921. And here is a picture of Einstein, and this is in the Shepherd Hall, and the CCNY president at that time, Mrs., was bringing Einstein out after a lecture, and I will show you a slide that gives you a little background on it. And this is the member of the physics department in those days, who is a friend of Einstein and also published a book on the general relativity based upon Einstein's work. That's how when Einstein arrived in New York, he did not go to Columbia, he did not go to NYU, he came to City College of New York, or in those days it's called College of the City of New York. All right, so this is what this Reinhard Wetzel did for CCNY. And then this guy on the left, I'm told, is Cohen. And do you know what is Cohen? Well, we don't know who is Cohen, but we know there's a Cohen library, right? Anyway, this for us, this is only relevant for us at CCNY. And I went to download from the website. And when did Einstein first visit City College? It was April 7, 1921. And he came and attended a lecture at the College of the City of New York. You notice he did not come to give a lecture, he attended a lecture. That shows something. By then he was already famous, right? Einstein is famous. And when he arrived in New York, there was a big reception in Battery Park, and the mayor of New York City and whoever else met him and welcomed him and gave him some kind of medal of honor from the New York City. So he is very famous, but did he go to Columbia? Did he go to NYU? No, he came to College of City of New York to attend a lecture. I was so impressed. This was first visit to any American academic institution and the first of 5 visits to City College. He didn't just simply come one day, he came 5 days. I guess that April 7 must be Monday or something like that. All right, so much of the credit for this is Reinhard Wetzel of the physics department, who was well acquainted. I just checked, he had actually published a book. The lecture was on general relativity. However, it was delivered by CCNY alumnus who happened to be Columbia University professor Kastner. And after Kastner's lecture, Einstein spoke for 20 minutes, during which he filled the blackboard with algebraic formula as part of his discussion of relative motion. All right, so basically, he did not say, you want to invite me? Don't let other people speak. let me be the star speaker. Did he say that? No, he says, ooh, there's a lecture at City College. Oh, my friend Wetzel invited me. Sure, I will come. Oh, even though it is not me, featuring me as the first speaker, featuring me as only after the lecture additional comments. That's okay. Einstein was ready to do that. And on Monday, I guess then after that attending, then on Monday, April 18th, he gave the first in a series of 4 consecutive afternoon lectures in Baskerville. The same Baskerville that you're going to have your final on December 15th. But anyway, so he gave the first in series of 4, and then the climax, the last 4, the fourth one, he gave it at the Great Hall of Shepherd. And this is the picture taken on that morning, Thursday morning, April 21st, 1921. And he was introduced by City College President Sidney Mezes, who introduced Dr. Einstein. And he spoke in German, of course, because at that time he did not speak English well, although later he did learn to speak English. And he says, I'm quoting from some record of it, I don't know the German words. It gives me the greatest pleasure on this, my first visit to America, to have this opportunity of meeting the student body of this great university. The student body of this great university. I appreciate very much your friendly reception and applause and extend to you all my heartiest good wishes. And according to this website, after this great big lecture in Great Hall, they brought Einstein over to Lewiston Stadium, which is where our North Academic Complex is today. And then they had a group photo with Einstein and everybody else, but somehow City College Library doesn't have that group photo. They only have this picture, but that's what it is. And now, since we do have a little time, you don't mind if I share a little bit about the history of Einstein's Nobel Prize? Do you want to hear that? I cannot. You chat. I cannot hear. Somebody has to say. What?
Sure.
Okay. Let me. It will take just 2 or 3 minutes. All right. For this general relativity, by 1921, Einstein was already so famous because all the astronomers and astrophysicists have confirmed it. He was so famous, but the Nobel Committee did not give it to him because they say, oh, they don't believe in the general relativity. There was some member of the committee that did not. But anyway, Einstein became very famous. And so finally, 1922, the Nobel Committee says, oh, we will give a Nobel Prize to Einstein, not for relativity, but for photoelectric effect. And so they gave a call to Albert Einstein. But you know where was Einstein at that time? He was on his way to Japan. And he actually passed through Singapore, because I'm from Singapore. And the historic record in Singapore is that when Einstein passed through Singapore, he gave a lecture to the Jews in Singapore, the Jewish community in Singapore. And he kind of like exhorted them because he wanted to raise money for Hebrew University in Jerusalem. And he was asking the people in Singapore and says, hey, I'm famous, but I am really caring for my ancestry. So donate to the Hebrew University in Jerusalem. But then he went on to Shanghai and then to Kyoto. And the call from the Nobel Committee reached him when he was in Shanghai. And the call is October You know, on Nobel Prize is announced in October. They called him October, and you know what he say? In order to receive your Nobel Prize, it would have to be December in Stockholm. But he says, I'm busy. My schedule is already well fixed. I cannot be there to receive the Nobel Prize at your ceremony on December whatever, 5th or 6th or 7th, right? I cannot be there. Sorry. But if you want to, according to my busy calendar, I will be Gothenburg in Sweden. I will be in Gothenburg in July of 22, I guess, 22, or the following year. If you want, you can give it to me there. Then. You got the idea? And what did the Nobel Committee say? Did the Nobel Committee say, you despise us? Forget it. We will give it to somebody else. Did Nobel Committee say that? Did Nobel Committee, huh? No.
No.
No. Why? Because the Nobel Foundation needs Einstein to boost up their, the glamour of the Nobel Prize, the glamour of Nobel Foundation, right? So they say, yes, of course. And so Einstein went with his rest of his busy schedule, and in July of the following year, not the December of the previous year, in July of the following year, he was at Gothenburg, and the Nobel Committee actually did come and say, here, Professor Einstein, here is your award for the Nobel Prize. But I am so very touched by what Einstein always, his heart is to be for his people, that he would raise money for the Hebrew University, that he would in fact come to City College because of his friend Betzel of the physics department. So his focus is not, oh, Columbia is so much more famous, oh, that NYU is that much more famous, therefore I should give them the honor. No, he is not. He is forever very concerned and helping others. And if later you ever come to another course on modern physics, you hear about Bose, Einstein-Bose statistics. Bose is somebody who is in Calcutta, an Indian physicist, but he wrote something which was also groundbreaking, but he needed Einstein to accept it for a publication. And Einstein, being a man so busy, indeed did look at this article from an unknown physicist from India. Who has ever heard of Calcutta? Well, he actually read that paper and recommended it, and then added his own contribution to it. So it now is known as Bose-Einstein statistics. But I have really gone over the time. I'm sorry about the technical difficulty, but I hope you get a sense. Relax. But what I hope I have been able to get you to grasp is, get the concept. Is this about Lorenz contraction? Is this about dilation? And then work on your algebra, your trigonometry, to then say, yeah, I will now know under this condition, I can then figure out what's the velocity. Or for interference, oh, that when it is path length difference is, integral multiple of lambda, it can be constructive or destructive, or due to what happened to wave 1 versus wave 2, and so on. So just grasp the concept and then apply it as the problem requires. Okay, so I'm sorry we ran over. Have a good day. See you on Monday. Okay, let me know. Yeah, I cannot see your chat, so.
Good night, Professor.
Okay, all right. So good night. Rest well. Huh?
Professor, quick question. This is Oscar. You told me to stay a few minutes after class. Do you mind
Right.
stopping the recording?
Okay, yeah, let me stop here.